Hello, everyone, and welcome to soils. And in order to understand soils, we need to review a little bit of weathering and erosion because soils are really one of the products of weathering in particular. And we have a nice little American sentence poem there to get us started. And yes, that really is a poem that is one sentence long, and it's really called an American sentence. Imagine that. Anyway, okay, so remember, let's just review a little bit. Remember that, and if I can get my slides advanced, there we go, that weathering is breaking geological materials down either physically or chemically. And erosion is then moving those materials from one place to another, right? And so when that water running over that rock dissolves some of the chemicals in it, that's chemical weathering. When rock gets broken down into little pieces, that's physical weathering. And then as all that stuff washes downstream or washes away, that's erosion, right? And so weathering and erosion. We've been through this before, but I'm going to hit it real quick because, like I said, soils are a result of weathering. So we want to make sure we remember this stuff. And so remember that there's two different kinds of weathering. I just mentioned mechanical or physical and chemical. Mechanical weathering, things like frost wedging, where freezing water expands and the rock breaks. Salt wedging, where salt crystals form and grow and pry the rock apart. Exfoliation, like at Stone Mountain or other large igneous bodies, where when you unload the rock, especially igneous rock, it expands and breaks off in these layers. I'll show you pictures here in a second. And then, of course, never discount the importance of biological activity, both chemically and physically, by the way, weathering rock. And then moving to chemical water, right? And I went through this whole thing with water where it's an acid, it's a base, it's both. And so if something dissolves in an acid, it dissolves in water. If something dissolves in a base, it dissolves in water. And so water in and of itself will break down rock. Given enough time. If it's hot, you need even less time, right? Water combines with carbon dioxide. That too should be a subscript, sorry, to make carbonic acid. And now you got acid breaking down rock, right? In Florida, water is acidified running through soil, causing acidic groundwater, which dissolves our limestone and creates our sinkholes and things like that that we're kind of famous for. And we'll do a whole thing about groundwater and karst topography where we talk more about that. And so a lot of times, you'll get a piece of rock where the outside is chemically weathered and the inside is not, right? Because it's protected from that. And I tell you what, I'm going to take 1 second and find y'all a picture of that. I will be right back, right back. And I'm back with a really nice picture of a weathering rind in a basalt. You can see that the outside looks very different from the inside, right? Chemical weathering is going to happen, on the surface of the rock and may penetrate some, but usually isn't going to penetrate all the way in, at least not right away and maybe not ever. And so what you have here is, a basalt on the inside and a weathered basalt on the outside. This is why geologists carry rock hammers in the field, right? You show us a rock, that's great. What's the inside look like? Because the outside is almost always altered in some way or another. You really want to look at that fresh surface. I mean, I would never look at that on the outside and say, oh yeah, that's a basalt. I have no idea what that thing is. Let me crack it open. Then it becomes obvious. So this chemical weathering can really wreak havoc with you in the field. Here's a nice rock in a glacial outwash plain showing frost wedging. All of this is course, physical weathering. Here's some nice foliation. I don't even remember where I found this picture. I don't know. I have no idea where it is. I didn't take it, but you see some really beautiful foliation. This isn't like bedding in a sedimentary rock, right? This is an igneous rock that has been unloaded and it's breaking, right? And it's breaking in these onion-like layers. And of course, don't underestimate the importance of water. This is a picture I took in the Pisgah National Forest, I believe. I forget where I was, but anyway, a little stream running through here is nice. It just reminds us that this water will dissolve anything given enough time. And so the role of water in chemical weathering, water plays an incredibly vital role in chemical weathering. But also notice the tree roots, right? These roots are breaking this rock open. Some things, lichens, like these lichens right here, can do a process called chelation, where they will literally pull chemicals out of the rock. They have a stronger affinity for the chemical than whatever chemical bonding is holding it in place, and so that's how you can get lichens growing on rock. They are chemically weathering the rock. And of course, if we're thinking about biology, if you've ever had a driveway underneath an oak tree, you know that trees can absolutely break apart rock. The way oak trees break apart concrete driveways and things like that. I know a lot of people with these really pretty driveways under these big oak trees that are absolutely wrecked by the roots of the trees. As we learned last time when we talked about sediment maturity, is that angular rocks tend to become more rounded and then more spherical, and we went through the whole scale for talking about angular or subangular or rounded or subrounded, and we kind of already know this stuff, but once again it plays very heavily into soil formation, so I just wanted to review a little bit. Not all rock weathers at the same rate, especially chemically or physically too, but right, they just don't, and so what's going to determine how quickly a rock weathers? Well, a couple of things. The first thing is just the characteristics of the rock itself, right? Rocks like limestone, they dissolve. Anything with soluble minerals or soluble chemicals will just dissolve, and so they will weather faster. The other thing is, if we just limit ourselves to silicate rocks or silicate minerals, mafic minerals are less stable and will weather faster. Okay, felsic minerals are more stable. Sorry, needed some water. Felsic minerals are more stable and will both chemically and physically weather slower. When you go to the beach, right, that sand on that beach is almost entirely quartz, which is, of course, the ultimate felsic mineral, being completely SiO2. So the characteristics of the rock matter. Right, and if we look, we can see this is kind of creepy, but one way to evaluate this kind of thing is to look at gravestones. And gravestones are interesting because they have very distinctive time markers, right? You know when this gravestone was set out. It was set out in 1868, right? You know what year that rock began its exposure to the elements, right? You don't, rocks in the field aren't printed with the year they became exposed, right? And so yeah, so yeah, the type of rock matters, right? I mean, here's a granite headstone set out in 1868, and here's a marble which has a lot of calcite in it that was set out in 1872. Look how chewed up this is and how not chewed up that is, right? Same time period. In fact, if anything, the chewed up one is a few years younger, but look how messed up it is, right? That has to do with the kind of rock, okay? And this is going to be important when we start talking about soils too, so let's keep this in mind. The other thing that will also be important when we start talking about soils is climate. Climate's very important, right? Climate, in determining soils, but also determining how a rock's going to weather, right? Temperature's important. Weather, especially when you're talking about chemical weathering, right? Because weathering is fundamentally a chemical process, and when you increase the temperature, the rate of all chemical processes increases. That's just kind of the rules. Okay, so when you increase the temperature, you increase the rate of all chemical reactions, and so temperature matters. Moisture also matters, right? Chemistry doesn't usually happen in the absence of water. right? So drier climates tend to have less chemical weathering. Okay, so if I could go back here, here we're talking about different kinds of rock, but you might also, if you didn't know the years, you might also just say, look, this is out in Arizona where it is maybe hot or dry, or maybe even somewhere, I don't know, further north where it's cold and dry, and this is down in the tropics where it's warm and wet, and they're the same. So in this case, it is the difference in the rock, but if the rocks weren't different and you saw this, you'd be going, okay, well, this is a climate issue, right? This is in a warmer, wetter climate, and the pristine one over here is in a cooler, drier climate, right? And so all these things kind of eventually fit together. So here's the most boring slide in the world. Sorry, I don't have a picture, or I could have the coolest picture. Hold on, I'm gonna go get a cool picture. Hold on, right back. Okay, that's better. So this is the Mars Curiosity rover, obviously on Mars, taking one of its famous selfies where it takes a bunch of pictures of itself, and then they can stitch them together to make it look like someone stood there and took the picture. No, no one stood there and took the picture, and yes, it's actually on Mars. The reason I'm showing it to you, though, is if you look at all that stuff around it, the stuff that's not rock is regolith. Regolith is just dirt, or just little ground up bits of rock. Okay, what it's not is soil. Okay, and people make this it's not, I wouldn't call it a mistake, but people are a little bit careless about this all the time, where they'll say the Martian soil, or the lunar, when they're talking about the moon, the lunar soil. I always cringe a little bit, because that's not soil. It's regolith, right? It's just ground up rock. Okay, soil has biology, right? Soil has organic material in it. Soil is alive. With all kinds of things, right? If we find soil on Mars, that's life on another planet, right? Or if we find evidence that there ever was soil on Mars, etc., etc. And so do me the favor, don't confuse them. I cringe a little bit when people say soil when they're talking about Mars or the moon or something like that, because it's not. It's regolith. Okay. So if we look at a graph here. There we go. Let me get rid of my rover. Soil has some mineral matter, and then it also has water, and about usually, I'm a little 5% organic matter is no. That number varies a lot, an awful lot. 5% actually no, 5% a worthless number. Pretend it's not there, right? Pretend that brown part of the graph is very, very changeable. It could go anywhere from 90 to 100% of the not air, not water component. In that case, it's called peat, or it could be zero. So yeah. But then there's some mineral matter, ground up rock, etc. And then there's some air. Air is very important. And then there's also water. Water is very important. And of course, they drew those arrows between the air and the water because the airspace can fill up with water, and then it can dry out, and then it can fill up, and then it can dry out. So those things kind of go back and forth. And as we'll see, that air-water space is vitally important, very important. And so soil is actually, we're not going to spend a whole lot of time on it. I'm honestly about halfway through my slides here. I'm not going to spend a whole lot of time on it, but it is very complicated stuff. This is one of the things that I do is I study ancient soils and nutrient cycles and insects and peat and things like that. So y'all have no idea how much I'm restraining myself here, but it's very complicated stuff. We're not going to get into the complicated bits, but it turns out that it is terribly complicated because soil is kind of an interface, right? Soil is where the geosphere, which would be the rocky parts of our planet, and the hydrosphere, which are the watery parts of our planet, the atmosphere, which is the gassy parts, and then the biosphere, which is that part of our planet that is life, right? Soil is where all of that meets. And so, when you talk to soil scientists, some of them are agriculture people, some of them are atmospheric people. Some of them are geologists. Some of them are, I mean, they come from all kinds of different backgrounds because it's all in there. One way or another, it's all meeting in soils, which is why they are so complicated, but also so very important, right? I mean, just the food alone, right, is we all like to eat, and so yeah, soils, right? So what are the things that control? I mean, they're complicated. We get that, but what are the things that control the formation of soils, or what kind of soil you're going to get, or how you're going to get a soil? Well, there's a few things. One of them is parent material, right? That's going to be the quote unquote bedrock, right? That rock that you start with. Right now, how fast the soil is going to form on that bedrock depends on the rate of weathering, right? Which is why I say, remember, everything you know about weathering now applies to soil formation. Right, and so is the rock mafic? Is the rock felsic? Is it in a warm, wet environment? Is it in a dry, cold environment? Is it in something in between? Right, all of that plays into now not just weathering but soil formation. Right, available nutrients are also important. Remember that a big part of remember. Let me go back here real quick. The biosphere, right? Soils are alive, right? And so for the sake of the plants and the animals and the other stuff in there, nutrients are going to be important. Mafic rocks are better. Mafic rocks have more diverse chemicals, more things that are useful as nutrients. And so remember, mafic rocks will also weather faster. They will provide more nutrients, right? And so yeah, right. Felsic rocks are, mostly silicon and oxygen. I can't think of an ecosystem where silicon and oxygen are limiting nutrients, right? That's not something that, organisms are like, gee, if I only had more silicon and oxygen. No, there's, right? No. Or, gee, I need some more magnesium, right? Or I need some more iron maybe, or something like that, right? And so mafic rocks with their more diverse chemical arrays are better for making soils than are felsic rocks, right? If I look here, here's a picture I took out at Stone Mountain, Georgia. You can see just that little stream running through there. Now, Stone Mountain's a granite, so it is felsic, right? Not a whole lot of nutrients. You can see you've got a very thin soil there. You can see the rock and you can see the leaves, and that's the soil. It's only a few inches thick. Very thin soil, right? It's a soil. You've got a little forest thing going there, but it's not very thick, right? And so, I would hate to even speculate how long it's been exposed, but it's been exposed for a while, and there's still no soil there, right? On the other hand, if we go to Hawaii, or there's some soil, but not much. On the other hand, if we go to Hawaii, we know that's a fairly young surface, right? Because Hawaii is a pretty active volcano, the Hawaiian Islands contain fairly active volcanoes, right? And yet, there's a thick, luscious soil there, right? Supporting all kinds of things. There's a rainforest there, right? And I promise you that surface is much younger than Stone Mountain, okay? But it was able to build a thicker, lusher soil because the rock is mafic, right? It's also very warm and very wet in Hawaii, at least on some sides of the mountain. There's a whole thing there, okay? But anyway, now I'm cheating a little bit. The Stone Mountain picture I took obviously in the winter, okay? But you get the idea, right? And so, yeah. The other thing, of course, biology. Oh my gosh, biology plays a huge role, and this would be, where my master's and my PhD work would come in. So I'm not gonna even go there. But biology is what makes soil, and what makes regolith, right? If it's regolith, it has no biology. If it's soil, you've got plant roots, you've got, worms and arthropods and, fungi and bacteria and all kinds of things, working their way through that soil, doing all kinds of things to it and making it soil rather than regolith, and recycling nutrients and, all kinds of things. Now, I'll just say, oh boy. Okay, so let me go back forward. There we go. Throughout the history of the planet, right, this soil community has changed, has evolved, right, and so okay, here we go. My master's and my doctorate in a very small nutshell. We have very, very thick coals, right, from about 300-ish million years ago. The reason we have thick coals is because this decomposer community was not as efficient back then as it is now. And so plant material accumulated, turned into peat, was compressed and turned into coal, right? I think I talked about this when I talked about coal, but if you've got a 10-meter coal seam, that means you had 100 meters of peat. Right, the compression ratio is about 10 to 1. There is nowhere on the planet these days where you have 100 meters of peat. You just don't. It just doesn't happen. It just doesn't happen because the decomposer community is so efficient, and so much more efficient. And so through time, this decomposer community has changed, and so soils have changed. And so there are things called paleosols, which are ancient soils, which people like to study because they're different from modern soils, because for a number of reasons. The plants were different, the decomposer community was different, and so it's a whole thing. Okay, I'm moving on now because I could keep on talking about that. Okay, the other thing that's important is topography. Right. The other thing, the other problem at Stone Mountain and in Hawaii, but it doesn't seem to be a problem in Hawaii, is those soils are forming on slopes, and so as material is weathered, it is eroded. Right. As that rock is broken down, it is then carried away. Right. If you have a slope. If you have a relatively flat surface, then the weathering happens, the erosion not so much, and so then you accumulate weathered material, and that starts making a soil. And so topography matters, right? We got a snazzy little diagram here, snazzy little diagram there, showing just a kind of a hypothetical area, and you can see that up here where the slope is very steep. Let me get some water. I'm going to cough. Make y'all think I have the plague or something. So up here, where the slope is very steep, you're not going to make a soil. Obviously, if it's vertical, you're really not going to make a soil. And you can see these little areas that are not quite so steep. They're making a wee bit of soil there, but not really much, right? Now up in here, you're going to get a pretty good soil. The slope isn't that steep. So you get some weathering in place, and so that's good. The problem up here is there's nothing washing in, right? There's going to be a wee bit washing out, but nothing washing in. So where's your really good soil? Down here by the river, right? Down here in this river valley, right? It's flat. You get material washing in. You get a river to provide moisture, right? This is why, when you look at Google Earth or when you look at maps, all this farmland is in river valleys. It just is. That's where the really good soil is, right? When I was in grad school at Texas A&M, the Brazos River was not right next to, but near school, and has a big floodplain, has a huge floodplain, we go driving down there, and you hit the floodplain, and suddenly it's all farms. It's just all farms. Where half a mile up outside the floodplain, it's foresty, mixed use, whatever. And then, man, you hit that floodplain, and it was just farm after farm after farm after farm, because that's where the good soil is. It's okay farming up here, and people do it. My grandpa did it, and it's just fine. But if the really good stuff is down in here along the river. Now, it's going to flood every now and then, so be ready for that. My grandpa had to deal with some of that too. But really, this is where you want to be farming, right? Just be ready for it to flood every now and then, But yeah, so slope is important. Topography and slope is important. Time is the other thing that people kind of always throw into this mix, and it is good to do so. I'm just going to be a little bit, I don't know, obtuse here and say that a lot of times people mention time as a factor. Time is not a factor as much as it is the factor that controls all the other factors, right? So parent material, biology, slope, climate, through time, right? And so you get all these things that act, and they act through time, right? One of my fancy soil instructors set up this weird derivative equation where everything happened through time. And so younger soils tend to be thinner and less well developed. Older soils tend to be thicker, right? All of these, and I mean, that just makes sense. I mean, it's not that fancy, but all of these processes happen through time, and the more time, the better. Okay. Now, once you start farming, then we got other things going on, drawing nutrients out and all kinds of stuff like that. But if you're just going to leave a soil alone and let it naturally do what it naturally does, it will get thicker and, quote unquote, better through time. So as soils develop, they develop a profile. They develop, if you go out and you just dig a hole somewhere, and if you want to, go dig a hole. It's kind of fun. Go dig a hole somewhere and look at the soil. Preferably someplace natural, right? If you go onto one of the SPC campuses and dig a hole, odds are you're digging down through topsoil or whatever that they've put there. Okay, so go out into the woods and dig a hole. Okay, although I have a funny story about that I might tell here in a minute. So anyway, okay, a soil as it's developing develops these layers that we call profile, and we can divide these up into a few different kinds of layers, or a few different layers, based on kind of what's going on and what's happening. Now, keep this in mind. The thickness of these layers varies tremendously from one place to another, right? I mean, some places don't even have all these layers, right? This is like this idealized textbook soil, right, that we always talk about, that you never actually see when you go into the field, okay? But we do have these layers, and they're called horizons. And so we begin. So the best way to think about soils is maybe think about them like a bunch of coffee in a filter in a drip coffee maker, right? Where it's easiest if you think of them from the top down, which is very unusual for geologists, because we usually think of things from the bottom up. But don't do that. Think of it from the top down, because what's happening here is the water is really what controls a lot of this. Okay, and so the water obviously goes from the top down. Okay, so the first layer we have is what's called the O horizon. O in this case actually stands for something. It stands for organic. Okay, and so the organic the O or organic horizon is this layer right here that is mostly decayed plant material. Okay, that's it. It's usually very thin. It's right there. If this layer is thick, then this soil is called a peat. Right, and now you can put it in your garden or compress it into coal or whatever. Okay, usually though, that O horizon is very, very thin. Now, the fact that I studied these peats kind of compels me to just tell you, just for fun, that you can, if you do have a very thick O horizon, you can actually subdivide that into the L, F, and H horizons. where the L horizon has almost complete, recognizable plant material. It's like, oh, look, a leaf, right? The F horizon has degraded plant material, and the H horizon is just this organic mush that we call humus. But like I said, this is a little too much inside baseball. O horizon is fine, right? Underneath the O horizon, you have the A horizon. Here you have mineral matter mixed in with organic matter, right? Because what's going to happen is the water is going to flow from the top to the bottom, and it's going to leach out some of that organic matter and wash it down here into the next layer down, which is the A horizon. And you can see they say here mixed with some humus. I almost said hummus, which is delicious but not a soil layer. But that's that H that we have right there for the humic layer of the peat bed. So anyway, so O horizon, lots of organic material. A horizon, lots of sorry. Lots of organic material washed down. Then we come to the E horizon, which is the zone of eluviation. We have two words. We're not going to really. We're going to use them. Here we go. Sorry. I shouldn't do this at night. Apparently. Okay. So the E horizon is a zone of eluviation. Eluviation is water removing material, either physically washing small particles out, okay, or chemically breaking stuff down and washing it out. But one way or another, here in the E horizon is the zone of eluviation. Okay. Next comes what's sometimes called the subsoil or the B horizon. I do not know why they messed up the lettering here. I get the O. Yeah, no, it doesn't make any sense. But E horizon is for eluviation. Now, if it was me, I would have named the next one the I horizon for illuviation with an I, which is washing material in, right? It's easy to remember. I for illuviation and I for in, right? And so material is being washed out of the E horizon into the B horizon, right? So this is the zone of eluviation. This is the zone of illuviation. Are your eyes rolling yet? I told you it was complicated, and we're not even doing the complicated stuff, okay? And then underneath that, you have the C horizon, which is just altered parent material, right? And then underneath that, you have the parent rock, right? The rock that the soil was built on. Okay, so this is sort of like I said, the literally textbook version of the OAE, BC, and then parent rock layers. Let's take a look at some soils real quick. Right, you go from this where you're like, okay, yeah, everything seems pretty straightforward, and then bam, oh no, nothing makes sense anymore, right? I mean, this is just, right, there's no layers here. This is important. This is heavily weathered clays and things like that, right? This one's in South Dakota where you can see, yeah, I got a really nice O horizon right here. Right, you got that really nice O horizon. You can see it right there, and then below that, there's the A horizon right there. Right, there's the zone of eluviation. There's the zone of right. You can see the different horizons. Now, I'm not going to show you any pictures and ask you, just show me where this is. Just know what they are. That'll be fine. But also be aware that a lot of times when you get out into the field, it's like, oh dang, I just learned all this stuff in class, and nothing out here looks like that. Right? Here's another nice one. You can see a nice little. Grasses tend to make peats. Actually, not thick ones, but they do tend to make peats. And so here's some more grass, and there's a little peat layer right there. And then there's the A horizon. And then there's the zone of eluviation. There's the zone of illuviation. There's the weathered bedrock, right? And so takes some getting used to. Definitely takes some getting used to. But there we go. Okay. Soil issues. I have a very boring slide ridden with words. Sorry. I just kind of threw them all on one slide. So soil's very delicate. right? It's biology. It's that mixture of biology and meteorology and hydrology and all these things. And so it can be very, very delicate, and it is obviously very, very important because we rely on it for all kinds of things. And so, what are some of the problems? Well, they are multitude. Soils are very touchy little things, right? Erosion, right? Poor farming practices can suddenly lead to erosion, right? The Dust Bowl of the 1920s, 1930s, where a tremendous amount of soil just blew away because farmers were using these terrible plowing techniques, right? It's not in the farmers' interest to lose the soil, so farmers they figured out how to do this, but you have to be very, very careful when you're plowing on slopes. When you're, I mean, you just have to be very careful that your soil doesn't literally get just washed away. Compaction is a huge problem in soils. If you have a friend who's a gardener, they'll tell you, and if you have a friend who's a gardener, go visit sometime and walk through their flower bed and watch what they do. They're gonna hate you, okay? Because not because you just you compacted the soil. Okay, remember that 25% water, 25% air, and that mixture back and forth? Yeah, you have to have that. You have to have that. This is why tractors have such wide wheels on them to distribute that weight so that as they're plowing and working in that field, they're compacting that soil less. And even with that, a lot of times with very old farms, you'll get something called a plow pan where the soil is incredibly compacted right below the depth that the plow reaches, right? Because years and years and years and years and years of running that tractor over that soil has compacted it, except for the top 3 feet or so that get plowed. So compaction is a huge problem. You ever notice sometimes if they don't build a sidewalk in the right place and people take shortcuts across the grass, eventually the grass will die? Okay, the grass isn't dying because it's being walked on. Grass actually kind of likes being walked on. Okay, the grass is dying because you're compacting the soil. And so the way you would have to fix that is you'd have to go in and like rototill up that path, to make that soil floofy again, to get the grass to grow. In fact, a lot of times when people build office parks and things like that, they don't build sidewalks right away. They wait and see where the grass dies, right? Because that's where people are walking, because that's where people need to go, and so that's where they need a sidewalk. But seriously, if you know someone who gardens or whatever, don't walk on their soil. They're not going to like you because you're compacting their soil, and that's bad. Irrigation is actually a problem. Rainwater is good, right? Farmers always prefer rainwater. Okay, but if they don't have rainwater and they have to irrigate, you might be pumping what you think is fresh water onto that soil, but it's not. It's got some salts in it, and I mean salts like just dissolved, not salt NaCl, but salts like chemical salts, just chemicals in the water. And so when you pump that irrigated water onto that field, if you have to do that too much, those salts will precipitate in that soil, and when that happens, you're done. You are absolutely done. And this is a huge problem in places like California where they're having to, they're trying to farm, but is basically in a desert and they're having to irrigate. You cannot afford to filter all that water. You just can't. And so they end up pumping, quote unquote, fresh water onto those fields. There's salts in that water, and it can be a real problem. It can be a real problem. Rainforest soils are interesting because most of the nutrients in a rainforest aren't in the soil, they're in the plants. And so when you go in and you cut down a rainforest to replace it with farmland, you're not going to be able to farm it for long, because when you took out all the trees, you took out all the plants. And so there's a very complicated a very complicated thing there about telling other people not to farm and stuff like that. But it is ultimately self defeating. Most once again, most of the nutrients in that rainforest are not in the soil; they're in the plants. Okay, and as such, next bullet point, removing plants. That's a problem, right? If you remove plants, you kill the soil. So, in places where you do a lot of logging or anything like that, and actually those two bullet points are kind of the same. Removing plants in rainforest soils, they're kind of the same. But, so you have to be very, very careful when you're logging, not to just cut down all the trees and take them out of the forest, right? That will kill your soil. You have to be very careful about that. So what you want to do, I mean, look, right? I'm not saying don't log. I live in a wooden house too. I mean, I use paper. I mean, there's all kinds of things, and trees are a renewable resource, right? You can plant more of them, and that's a good thing. And so, but you want to be very, very careful about how you harvest them. You want to do something called uneven age harvesting, where you go in and you take a few, but you leave a few, and then also you have no use for the branches. Strip the branches off of the tree before you take the trunk out of the forest, right? Because that'll leave those nutrients to decompose and be returned to the biosphere. Forest ecologists call fallen trees big dead wood, and it's very important because big dead wood, fallen trees decompose and return nutrients to the soil and to the biosphere. And so removing plant material from forests, even plant material that's just fallen on the forest floor, is bad. Okay, it's just you don't want to do that if you can. Now, once again, yes, I live in a wooden house. I mean, I'm not saying don't ever cut down a tree, but I'm saying do it in a smart way as much as possible. And then lust, not what you think it is, leaking underground storage tanks. Oh my gosh, old underground storage tanks, they rust, they fall apart underground, and then whatever toxic stuff was in that storage tank is suddenly in the soil. And that is a huge problem. A huge problem. There's a whole government thing called the Superfund meant to clean that stuff up. It is just a massive problem. So yeah. Okay, so I'm under time, and I promise you a story about soils. I was taking a soil science class at Texas A&M. It was a forest soil class, and so we took a field trip out into the woods, where we started, of course, digging a hole, because that's what you do. So you need the hole to be kind of long, though. It's more of a trench. And so we're digging this, I don't know, about 6-8 foot long trench out in the woods, and it's a couple feet wide, and it gets to be a few feet deep, and there were only like 3 of us, right? And so it wasn't that small a class, but not everyone could make the field trip. So it was like me and the professor and a couple other people, not many of us. And so we're out there digging this trench in the woods, and next thing I know, the county sheriff shows up, really curious about why we're out here in the middle of the woods digging what looks to him to be a grave. And so there was some real curiosity on his part about what it was we were doing out there. It didn't take long to sort it out, but he was like, "You mind if I look in the trunk?" And we're like, "You definitely need to look in the trunk, because there's nothing going on here. You're just going to find more shovels and soil testing equipment." So eventually, I mean, it didn't take long to sort it out, but there were definitely a few anxious moments when the police officer pulls up with his lights on, and we suddenly realize that we're digging a grave in the woods, or at least what looks a lot like a grave. Fun times doing geology. Okay, that was short. Yay for short. So there's soils. Much more complicated than this, but I really wanted to restrain myself. So anyway, I'll shut this down. I'll get it uploaded, and I'll start working on the next one. Okay, guys, take care. Bye-bye.